Okay, hey everyone. So Serena called this multiple times a VLA lecture. I wouldn't call it as much as a lecture, but more like an inspirational keynote to all of you. So, but let's just start, and you're going to see what I mean. So, are intelligent robots the next industrial revolution? Before we answer the question, quick question to you: how many of you have trained your own VLA? How many have tried? So, why do I not see all your hands up? Right, so like this is, and I think like it's kind of, that is the question that I want you to basically eliminate like at the end of the lecture, right? So, well, what are intelligent robots the next industrial revolution? Boring question, right? But why do we actually ask this? Because we see these amazing videos on Twitter and everywhere, right? Like, so we have like those really amazing acrobatic feats from very sophisticated hardware, which again, is very impressive, right? No shade there. But one of the issues is that oftentimes you see basically the robots just interacting with themselves in some very, very rigid environment, like walls or like the floor, the ground, these kind of things. There is no complex manipulation there, right? We actually see like a change in that a little bit. So we actually can see these robots using their whole morphology, like the atlas on the bottom here, in order to do like some industrial tasks. Or we have the figure robot that actually is manipulating kitchens. But honestly, my kitchen does not look like that. I don't know about your kitchen, but that thing is like, I don't know. I don't even think kitchens in the store look like that, right? So again, we're not quite there yet. At the same time, we actually see this really impressive behavior generation, right? That we have from like research from like top left TRI or Google, DeepMind, right? Or Generalist or physical intelligence here, right? So we can see that we actually start seeing robots being useful in day-to-day tasks, right? Like, and not useful, but very, very good. But it doesn't really feel like they're basically ready to get out there, right? Nevertheless, this combination of the sophisticated hardware and this sophisticated, like, let's say, intelligent approaches, right? Or behavior generation approaches actually like gives us a lot of hope, right, for the future. So, and underlying all of this is basically this new like wave of generative AI. And we saw before the talking a lot about generative AI, so I will be very brief on this. But I think like two things that we need to like acknowledge is basically like the language generation part. So we have ChatGPT, Claude, Gemini, and others there, right? Like the Gwen models should also be mentioned up here actually. But so that is really, really great. But we can also use them to generate images. So for instance, this is like an image of Germany winning against Paraguay in the penalty shootout, which brings us to the topic of hallucination. In this case, more like human hallucination, right? So I don't know what happened here, but like, yeah. So obviously you can still see it's like very high fidelity, realistic and so on. So generative images, like, or generative AI is actually like very, very strong, very capable here, right? And we basically encapsulate all of this in what we call foundation models. Now the question for us as roboticists becomes like, okay, can we actually do something similar for behavior generation, so-called behavior foundation models? So we want to have humans doing their everyday tasks, right? In the wild data, we heard about this earlier today, right? And then have robots learn from these observations or from demonstrations or from interactions and doing the same chores that we are tired of doing, right? Be it in a household or like also in industrial settings. So the question is now, how do we get there? But once we have that, the question, are intelligent robots the next industrial revolution? We can answer with yes. And with this, we're done for today. So if you have any questions, we have like, I think 80 more minutes left, right? Thank you. Now, obviously, if you, like, most of you are not old enough to remember tartar sauce, or also known as grumpy cat, right? But if you're a little bit AI grumpy, you might say like, well, I mean here, right? As academics, as like, or in Europe in particular, how can we even compete? Because everything I've showed you, right, was basically industrially driven or like very well-funded startups, right? And when I say well-funded, we're talking about millions, if not billions, right? So we don't have the resources to do this. So generally right now, and this goes to basically your hand raising earlier, like the consensus is that we just cannot compete. So we just don't. Right? And that is, I think, a very dangerous perspective. So today, I basically want to change the narrative. I want to ask the question rather, not how can we compete, but what will be our impact, right? So as a pro-AI advocate here. And since we're in France, I was thinking we're going to give it a little bit of a motive, so we don't just accept the tyranny of the status quo, but it's time for a revolution, right? Again, to clarify, since we're friends, this is not a call to violence, right? Just saying, there's other ways of starting revolutions. So, yeah. Anyway, so let's talk about this. So the actual talk today is towards on-premise behavior foundation models. And why on-premise is so important here, we will see right away, right? So if we actually take our behavior foundation model, I'm currently argued that there's 4 major barriers that prevent us from actually using this in like academic settings or like with few resources. And the first one is the resource barrier itself, right? So the size of these models, the training and the inference compute that we require, right? So that is like already like one of the major challenges why a lot of us cannot even run these models at home or whatever, right? The second one is the data barrier. So we heard earlier today, again, how important data is and how much data we need and what all the things that we need to do with the data in order to make it useful. And I just think that's, while it's true, I don't like it, right? So we need to be more like able to just use data the way it is, right? Like learn from bad demonstrations, right? So not go through your data, right? And only take the recovery states, but actually learn from bad demonstrations. We need to have like more efficient ways of label this data, right? Or curate it rather. So we need to address that barrier too. Then also now that we're actually moving into the physical domain, right? There is actual issues that we also need to address when deploying this on physical hardware, on robots, right? So one is that we need accuracy. So the robot needs to be able to actually pick things up properly, right? So there's no like sense of accuracy in the physical sense in like pure VLM models. But also, if we actually deploy this robot, we have things like sensor fragility. So the sensors might break, or there might be a lot of noise, or there might be other sources why the actual input coming into the model is not as good as like a pure VLM would expect them like an image to be, right? These kind of things. And finally, we need to be much, much faster. I mean, if we're talking about like 0.5 seconds for time to next token, right? So basically I ask the robot something or the VLM something and I get my response within half a second. We actually think that's really fast, but for a robot that's horribly slow, right? So we need to be much, much faster in terms of producing reactive behavior. And finally, something that some of my colleagues will actually challenge, like, or don't see it as important, but I really stand behind it, is that we also should address the interpretability barrier. Meaning that if we actually deploy these models on robots that interact with us or help us in the environment or at home, we also need to somewhat understand why they do what they do. We might not need to understand every single neuron in the model, but maybe some like checkpoints along the way or something that we can actually like pinpoint and say like, okay, oh, you thought this object was important? It's actually not, right? So you clearly overfitted to some other prior data or misunderstood the task or something like this, right? So we actually need to have this barrier addressed too. And once we actually get rid of all of those 4 barriers, what we're left with is what I call on-premise behavior foundation models. So my revolution, right, the one that I'm trying to start is that instead of just going along and like having larger models, more data, and like trying to outpace like competitors in a game that they design, we actually focus on those barriers, make basically our own standpoint here and say like, okay, if we actually cannot out data and out compute the others, maybe we out, like, I don't want to say smart, but like outsmart them, right? So not saying the others are not smart, they're very smart, right? But we basically need to take our minus that we have and turn it into a plus. We just need to find this additional little dash, right? Okay. So with this, let's dive directly in. Foundation models, what do we mean when we say foundation models? There's many definitions out there, right? You see a lot. So this is pretty much taken from the seminal Stanford paper, right? Foundation models are generative AI systems pre-trained on diverse multimodal data that can be adapted to perform a wide range of downstream tasks. Realize that nothing here says they have to be huge models, and nothing here says that there has to be huge data sources, right? So yeah, so what kind of generative AI systems do we know? LLMs and VLMs, which are really, really good at creative text generation, conversational abilities, but also to a certain degree, like are very good in semantic understanding and even reasoning or task decomposition, these kind of things, right? I say to a certain degree because very often they're actually lacking this little bit of physical intuition, right? Like this little bit of actually knowing the physical world, geometry, these kind of things, right? To do proper spatial or temporal spatial reasoning. And then also on the other side, we have diffusion or flow matching models, which are great in generating high fidelity data, right? So things that is like maybe even a bit more complex to generate than just next tokens. So we can use those, for instance, to generate like amazing like medieval scenes or like anime style images, or like the Karlsruhe Schloss in a Wes Anderson movie, cats that can defend against acrobatic robots with laser swords, and Iron Man ironing, ironically, right? So we can do amazing stuff with these generative models. So how do we turn them into behavior foundation models? We start with these approaches, right, or with these clusters of approaches, and then diffusion models, if we actually retrain them in order to produce behavior, as we've seen again earlier today, we end up with diffusion policies. If we do the same thing with LLMs or VLMs, we end up with so-called VLA, or Vision Language Action Models. We can combine these approaches to so-called VLA flow matching approaches, for instance, Pi0, right, or Flower, as we'll see later. And then finally, in order to actually make the models understand that they're supposed to generate actions now or behavior, we need something that represents those within a, like, let's say, a form that is understandable to those models, right? And we call this often action tokenization. So we're going to talk about all of this. We're going to start with Bezo, which is a little bit of an older work, right? So Serena introduced me already with like Flower, but before there was Flower, there was Bezo, right? Bezo was basically our approach on diffusion policies that we also developed contemporarily. But diffusion, I'm going to be very quick because we had a great tutorial or great lecture earlier today, right? In a nutshell, the idea is that if we actually have some unstructured, some very structured but unknown distribution and we want to generate samples from it, we cannot, right? So there's no clear way of how to sample like cute dogs on couches or cute dogs on the floor, right? These kind of things, like what are the parameters underneath it? We don't know. But if we keep adding noise to it, right, the images or the samples start to look more and more like, all the way to something that looks quasi-Gaussian, right? And we can very easily draw samples from the Gaussian. Now the question becomes, if we do this by adding noise, maybe we can just learn how to undo that noise addition, right? And then go from a sample on the Gaussian back to this high fidelity sample from this structured but unknown distribution, right? And that's basically what diffusion and denoising does in that sense. And what I just showed you here is basically what we refer to as the DDPM-based diffusion model, inspired, or can also be interpreted as like hierarchical VAEs, variational autoencoders and so on, right? So where we have discretized time steps in order to go from structure to noise and back, right? And that is like the type of diffusion that diffusion policies by Changqi and Shoran Song was originally like structured around together with TRI. Very impressive, amazing work. At the same time, same conference, we actually introduced our approach, which is goal-conditioned imitation learning. And the difference between them is that while DDPM has the discretized time steps, right, in the diffusion process, we actually use continuous time steps or so-called score-based diffusion models. So, and I kind of want to explain to you a little bit the advantages of that and why this is good to know, right? So we base our work on work from Yang Song and Tara Karas, so-called EDM-based diffusion policies. EDM is the abbreviation that people chose for elucidating design spaces of generative models. EDM, elucidating design models, right? Yeah, but in a nutshell, again, because we had the tutorial already earlier, so I'm going to be a bit brief here. We have the same idea as before. But now, instead of doing this step by step, we actually describe this whole thing as a stochastic differential equation, right? With F being the drift vector and G being our noise injection here. And the amazing thing is that Anderson in '82 already explained that for every forward SDE, there exists a reverse SDE. And that sounds a bit weird, right? But like what this actually means is that purely in math, right? That means that like if there is a way to go from structure to noise, described as an SDE, which there is, right? Which we can. There is another SDE, right, which can go the exact opposite way. The only problem with this is this little fella on the bottom here called score function, right? And that thing usually is not like analytically solvable, right? So this is what prevented people from doing this like years ago. But now through like deep learning and like transformers and like generative AI and so on, and all the other insights that we gained in the last couple of years, we actually have a way of training the score function directly. And this is what diffusion models do. Even the DDPM-based diffusion models intrinsically learn this score function. And then we just follow the SDE back to our noise. So in a nutshell, this is what it looks like, right? So we have our structure. We want to generate an image, but we cannot, right? So instead, we just draw a sample from our known distribution, and then because we have learned the reverse SDE, we create a sample and like denoise the sample all the way down to our actual structured sample, or the one that we actually care about. Okay. So, and we can do the same thing for behavior. So behavior in itself is also like a very highly like structured but unknown distribution, and the question is how can we actually go through that, right? So yeah. So what did this buy us? So first of all, any questions at any point, right? Like just interrupt me. But this should be very familiar, right? Given the tutorial that we saw, or the lecture that we saw before. So this is great. So what does our forward SDE actually look like? And I'm going to be again very, very brief here. But in a nutshell, this is the forward SDE, and the beauty of basically structuring our drift term and our noise injection like that is that the reverse SDE actually looks almost identical, right? Which again gives very, very nice properties in terms of like training these type of models, right? So it's basically just like a different sign on one of the parameters, right? And we're pretty much good otherwise. So again, like you will get the slides and then you can actually look at it yourself and derive it. But another thing that is important to note is that we don't actually optimize or basically look at all of this equation as the model. The model in itself, right? And when I say model, I mean the neural network is much, much simpler and smaller, right? But it's an essential part of this SDE, right? So the score model actually that we use, again following the EDM model, at the end of the day basically just determines some noise, right? Again, similar to the DPM, but now with this SDE in mind. So I would actually encourage you to derive this training objective yourself. There is amazing technical paper by Pascal Vincent that actually does all of this score-based loss derivation. So go ahead, do this. But as I said, I want to be very brief on the diffusion part here. One thing to mention, because this came up in the tutorial before, or in the lecture before, yes, like there is an SDE underlying diffusion and also flow, like, well, not flow, but underlying diffusion. But in practice, we don't actually use this. In practice, for behavior generation, for image generation, we do. For behavior generation, we actually most of the time just use the so-called probability flow ODE, which then actually gets rid of the noise, right? And becomes an ordinary differential equation. So in this case, actually, there isn't that much difference to flow matching anymore. And in fact, that the way that we actually use it with score-based diffusion, right? Score-based diffusion, it's the same as flow matching if you consider that your noise that you inject is Gaussian. So as long as it's like Gaussian, you can literally show that it's mathematically equivalent. There's two amazing papers that you can have a look at, right, that do exactly that, right? But yeah, score-based diffusion and flow matching with Gaussian noise, pretty much the same. So now, where do we get actually the samples from this distribution from in our case? We do goal conditioned diffusion here. So basically the idea is that once you actually have your samples, right, or your trajectory, you take like some state action pairs as your current state, right? And then take some state in the future as a potential goal. So what this means is that you know exactly that where you are right now, there is a path, right? There is a path that will lead you to this goal, right? And then it's like your job, or the model's job, to learn what the actions would be in order to transition to state to state to state to end up at that goal. But this way, just from given demonstrations, we actually can do this goal conditioning. So why do I bring this up here? Because again, we heard in the previous lecture that, previous presentation, that data and this data sets are very, very important. But if you actually are supposed to do the same task 10 times, you get annoyed. If you have to do it 100 times, you get aggressive. And if you do it 1,000 times, you get homicidal, right? Like, so don't do this. So instead, what we do here, in this case, is actually learning from play. So you actually just release the human into the scene and say, like, do whatever you want, right? And the human just does demonstrations with the robot, shows their creativity, right? Like shows how they can actually solve tasks in different ways, but also shows transitional states, basically going from one task to another, shows recovery state because something goes wrong. And it's not that we label it as a wrong demonstration, right? We don't label it as anything. But now we need, of course, another way of using this data because we don't label it, right? We don't say this is how you do task X, how you do task Y. And that is where the goal comes in, right? And this is how we can, again, be much, much more efficient with data generation here. So for single actions, this works really well. And even for action chunks, it works really, really well too. So one thing that I just quickly want to still mention, and I just want to be sure that I actually need to speed up a little bit, one thing that I quickly want to mention too also is that we also have something called compositionality now in these approaches. Given that we actually represent everything as so-called score functions, we can now take our demonstrations as we had. As I mentioned, we have a goal now. So the policy that we learn seems to always require a goal, right? However, if I'm at home, I don't want to tell the robot every time what to do. Sometimes I want the robot to do what I tell it. I say hey, clean up the kitchen. Then the robot cleans up the kitchen. But sometimes I want the robot to pass the kitchen, see that it's dirty, and clean it by itself. Does it make sense? So sometimes I don't have the goal, right? The beautiful thing is now that by just pretending that 10% of our data doesn't have a goal, right? We can actually train a policy at the same time that is goal independent. So whenever we don't want to give an explicit goal to the robot, we just say oh, this is a non-goal token, and then the robot does whatever the robot does, right? And we can now, and this is again the beauty of compositionality here, we can now combine those two policies, like the goal-dependent one and the goal-independent one, during runtime without retraining. So we can now actually take some factor, lambda, and we can play around with it, and then make it either follow exactly our instruction or do explorative tasks, right? And we can see this basically on the plot on the left-hand side, right? If we actually choose lambda very high, right, then it actually gets very clearly towards only one state on the right-hand side, right? And if we basically choose lower, then it actually gets, or then it actually spreads out and does more explorative work. So this was actually also followed up by dear colleagues of ours, right? So you can see actually we start to have impact, right? So we actually think about things in a different way, right? And that actually also allows us already to see that other people will pick up on it. The bottom one, by the way, got the best paper award at AIxHRI in 24, right? So I'm gonna hurry up a little bit. This took longer than I actually wanted to spend on it. But one thing that I still wanted to show you, which is really, really amazing, is that we actually can outperform DDPM-based diffusion policies with only 5 denoising steps, right? Because again, in image generation, T is often at 1,000. In behavior generation, we're at 50. And we actually need only 3 to 5 denoising steps on all benchmarks and still outperform DDPM-based approaches, left and right. So, but again, this is by now quite a bit older work, right? But not not to say it's bad. So please go ahead, take a look at it. I think this is still worth looking at. So now, moving on, picking up a little bit of pace. The next thing before we actually can go towards VLAs, right, is to include language into our behavior generation now. However, if we actually want to train on language annotation and you look at the data sets available, there's only roughly 10% of all the data sets available that have language annotations. Or actually, let me rephrase this. Of all the data sets and all the data points in the data sets, only 10% of those data points have actual language annotations, right? And that is quite a problem. So these days, it actually becomes better, right? But back then, or still, it's not ideal. So what most approaches do is then we only train on those 10 data points. But again, we actually learned that we need more data, right? We need more data to learn better behavior or generalize across behavior better, right? So how can we actually leverage the entire data set? And this is where MDT comes in. So the idea is that we introduce 2 additional objectives here, right? One called contrastive latent alignment and the other mass generative foresight, and add that to Bezo in order to train the model such that it can learn both on language and non-language data. And we're going to do this very quick on 2 slides, right? So the idea is now in contrastive latent alignment that if I have demonstrations, right, where there is language, so one of those 10%, I can actually say okay, I have my current state, I have this goal image, right, so the goal state, and in addition, I have this language goal. So if I consider now only the goal image, and I basically encode this in our policy space, we might see that this is somewhere in our latent space, existing here for its top right. At the same time, if I do the same thing, the same demonstrations, but now instead of using the goal image, I use the goal description, so the language, right, and project that into a latent space, that might actually be somewhere else, but should it? Right? And we argue it should be much, much closer to each other, right? So it doesn't have to be identical, overlapping, but it should definitely be closer to each other than it usually is. So what we do is that we introduce this contrastive latent alignment loss that actually pushes demonstrations where the goal, which have language, right, closer together between the goal image and the language image, the goal language, right? And demonstrations of other tasks, right, where there's a different language or a different goal image, get pushed away. So in this way, basically, we align language and images in the goal state closer to each other. It's like a loss that you guys know from clip, right, or other like embeddings like this, which works really well. What we did is we argued that this is not sufficient in the encoder. This has to happen in the policy space, right before we generate the actual behavior. And the second thing is master into foresight. There, the idea is that we do not only want to produce action, but usually when you use something like clip or like Voltron, they're very good on static images, but they're actually very bad on moving images, so they don't understand dynamics. And to this day, even like some might argue that VLMs don't understand dynamics necessarily by themselves, right? So how do we actually enforce this understanding of dynamics? We said like, okay, you get the current image, you get the goal description, and now predict like scenes or patches of a future potential state, right? Why do we patches and not the entire image? That has to do basically with like distractors, right? So if you do the whole image, it might focus on reconstructing or generating parts of the state space that are not relevant for the task. If you do patches, you actually average those distractors out. And that's all it is, right? We basically just randomly take away some of the patches, right? And tell it like fill the gaps. Like fill the gaps, that's the additional loss that you have. And if you think about it, predicting future states of the environment within the latent space of the behavior model, what does that sound like? That's a world model, yeah. It sounds a lot like a world action model, right? And we did this like in 24, like on a smaller scale, but I know for a fact that some of our big company friends are actually taking this actual approach and extending it much more. Yeah, and we can actually see with exactly that, the benefits that people also say now about world models, because it understands the dynamics, right? It actually requires significantly fewer data points in order to generate much better behavior, right? Some other dear friends actually took this one step further and used it for not predicting actions, but videos, right? And used the same approach for video generation. Okay. The interesting thing here is that language doesn't have to be the scarce label here. We use language because we want to go towards behavior foundation models like VLAs and so on, right? But it can also be something else. So if you, for instance, have like complicated sensors like LiDARs or like other like things that are much more expensive in data collection, but the information that they achieve is also available in a cheap sensor, just not as readily available, right? You can use the same thing. You can do this with like thermal sensing, you can do this with like LiDAR, you can do this with like other event cameras, other kind of sensors, right? And pair them with like cheap RGB data. The only thing that is required is basically that you have actually the information that you want to extract in your cheaper sensor present. So there is a way to extract this information. Otherwise, this wouldn't work, right? Yeah, and that was like 2 years ago. So now, real quick, before we finally got to the VLA, one last part that I also, again, want to show and use here for you to see how we can actually think about problems in a different way, right? And solve these problems that others don't think about. Something that nobody thought about so far, right? Like, or until we did in this, is that right now, this multimodal input, I said nobody, but at least there was no widespread work on this, right? And I still don't know any good follow-ups on that work. But let's assume we're doing multimodal models, right? We have different images, in this case, different perspectives, representing different modes, right, of this simple scene. Usually, all of the approaches assume, like the VLMs, since they have been trained on it, right, that these images always are present all the time and noise-free, right? Does it make sense? So you train this in your data set, you have these images, right, and they just exist there. So when you train your model, that's the input that it gets. What happens if one of them fails now? What happens? Any question? Or any idea, any thought? Well, the model doesn't know how to deal with it. So for the model, right, if it wasn't trained on it, it just means that for this one sensor, it's night, right? Everything is dark or whatever, right? So it's pretty bad, right? So I don't want a robot like this driving around at home, right? I want the robot to be more robust to the sensor failures. So now you might say like, well, but you could just do dropout, right? You could just say like, oh, like similar to what we did with the goals, like every once in a while, every few data points and so on, you just say like, there is no information. Yeah, you could do so, but there's a fundamental problem in how we train these models that basically like leads to dropout not being the solution. And the fundamental problem is that when we train these models, right, there is an incentive, right, that each sensor gets basically the bit to produce one part of the information in the latent space. There is no reason, right, why multiple sensors should produce the same information. Actually, it's like discouraged, right? Because it would be inefficient. You have a limited amount of parameters, right? You want your parameters to be like really like well used, well utilized, right? So if one sensor, or like if I can get this piece of information always from one sensor, why should another sensor even produce the same information? There's no point in it. Does it make sense? So even dropout, and we can see this in the latent space, produces these clustered, like, or these clusters in the latent space, right? Which is not good. Because that exactly means if that camera on the bottom left goes missing, then all of the red information is gone, right? Even though maybe another sensor could have delivered the same information. Does it make sense? So what we do instead is that what we want instead is actually we want to consider shared and private information, right? So we want clusters where there is this separate like information, right, that only one sensor can provide. But if there is information that can be shared, it should be between them, right? Does it make sense? So we do this basically by explicitly including into our loss function shared and private embeddings, such that we cannot recover the entire image, right? But we can recover part of the information that is gone. So, just as an example for private and shared embeddings, right? So the two images on the right hand both see where the rim is, for instance, right? Whereas only the one on the left hand, like left top, can see the base of the robot, right? So this would be an example for private and for shared information. Okay, so we train this, again, I'm going to be very quick here now. We train this with an info-NCE loss, where we basically say like the different, so for the shared embedding, different camera, same time step, like that is an example where there should be shared information existing if it exists, right? And like different camera at different time step, we just assume that there is no shared information. Similarly to, for the private, but the other way around, right? The same camera at a different time step should still see the private information, right? Whereas a different camera at a different time step should not see the private information, right? So with this, we add these type of losses to our already existing diffusion loss, right? So we call this the disentanglement loss because it disentangles the latent space now, and we train our diffusion model just based on that. And what we can see is that it actually performs really, really well across multiple experiments here, right? Which is really, really neat. And in fact, it even is still usable if two of the sensors drop. So if we have, in this case, for instance, like two sensors completely masked out, so completely gone, we still have around 20% success rate, which is pretty nuts, right? So this is actually quite nice. And in addition, what we saw is that the later representations that we learn apparently allow it to be much more robust towards perturbed demonstrations, right? So if we actually now change part of the state space, right, significantly, for instance, through this Colosseum benchmark, we actually also perform much better there than competitors. I wouldn't go as far and say like that there is no interpretability, but there's a little bit of illusion of interpretability, right? So we can actually see that, for instance, some private embeddings are that in the disentanglement loss, only this, you can see my cursor, I believe, only this part here ever sees the end effector. So it focuses its private embedding on the end effector. Okay. So with this, finally, now, after half an hour, we finally go to our first VLAs. So, let's say we start scaling up first, because like the last thing that I actually want to mention right before this, because all of this is a prelude to this, is that if we now actually want to keep using diffusion, but we want to scale it up, right? For instance, because we want to use it in a big foundation model, right, or a behavior foundation model, we have one big issue. What is the big issue with diffusion and foundation models? If we want to scale it up. So what is the one big downside that we've heard of diffusion models, and to be honest, also with flow matching?
Inference speed.
Why? Inference speed is correct, but why? What makes inference slow? Who said it?
You have to query the model multiple times.
Exactly, that's a problem, right? Because if I now want to increase my parameter space, because I want to encapsulate more of the parameters, more of the things that are like found in the real world, right? And I increase my parameter space by, let's say, only 10, but I have to go only 10 times through the model, my compute complexity goes up by 100, right? And now we don't scale up by 10, we scale up by 100, and we need to go 100 times through the model, right? You can see how this is becomes not sustainable. So we need a better way to actually deal with this inference cost, right? With this iterative inference that we do there. So what would be a more efficient way of doing this? If you actually consider the denoising process, right, the diffusion process, something that we realized is that this is actually a multitask problem, right? Not diffusion for multitasks. Diffusion in itself is a multitask problem. The denoising problem is a multitask problem, right? What do I mean by this? Well, imagine you're a sculptor, right? So this is your completely unstructured noise distribution, right? So your Gaussian or whatever, right? And so this is represented by a big block, right, of stone. So at the beginning, you want to get rid of a lot of noise, right? So at the beginning, you just want to basically get roughly the structure of your distribution, right? So you use one type of chisel, right? You use this chisel basically that allows you to cut off big chunks, right? That's one task. Task for one tool. Task, tool, expert, all of those are synonymous here, right? But later on, right, if you actually want to turn this into like a masterpiece, right, you need to add detail to it, right? You need to remove specific noise, right? Like you want to make it accurate, you want to make it high fidelity, right? So you need a different tool for this. She's not even looking. And then you actually end up at this masterpiece that is a bust of Serena, right? So basically, but you understand the difference, right? So at different stages of your denoising process, you need the different tools, different experts. And that's exactly what we do here, right? So we still increase our parameters overall, but instead of like having just like a lot of parameters here, we say that we split up the parameter space and allocate certain parameters for different noise or denoising experts, and have then in addition also a router which basically determines which expert to choose when. All of this is data driven, right? And then during the denoising, during the inference then, it becomes deterministic, so we even can get rid of the router. But during the denoising process, the router basically says like, okay, for this noise level, so we're basically at the beginning of a denoising process, we're gonna choose this expert. For like later on, we're gonna choose another one, right? And what this does is really, really like amazing. So basically, on the left-hand side, you see inference time in seconds, but on the right-hand side, you see the actual G-flops. So better hardware, or weaker hardware, doesn't matter. This is the floating point operations that you need to do in order to get to the same results, right? Where we have, like in green, our dense parameter. In yellow, we have basically mode, so basically just like this choosing of different experts for these different noise levels, right? And in blue, we have mode with cache, which basically means that after we trained our model, the model knows, right, which parameters to pick, right, or which experts to pick for which noise level. So we can actually always stack them together. We can stack them together and basically build up a cache, so we get rid of the router, and we can actually simplify the denoising even further, right? So, and the amazing thing here is also like that we outperform several benchmarks, right, or models on like several baselines with like just a fraction of the necessary training compute now, right? Because we can actually scale it up without having to worry too much about this computational problem. Overall, the structure, like depicted again on the top left, right? Again, the router in this case only cares about the noise level, right? So this has nothing to do with multitask in terms of like the robot doing different tasks, right? So this is very important to clarify. Okay, so and again, follow up. What some of you might know. How many of you know WAN, the video generation model? Okay, this is one of the two most used open source video generation models. By now it's at 2.8, I think, or I think 2.6 or 2.8. And since version 2.2, right, they actually use this mixture of expert denoising approach, right? So now finally VLAs, right? So we now know how to scale up like denoising, right? We know how to use this efficiently. But one thing where we have this big problem here is that all the work that we talked about so far used like clip encoder or Voltron encoder or anything like that, right? Like so even sometimes you can just arrest that. And the problem is if we actually want to have complicated scene understanding in here, right? Then we run into an issue, right? Because we need like something that is actually trained on much, much larger data sets and with some reasoning capabilities, these kind of things. Does it make sense? Okay, so what can we do? Naturally, instead of using Voltron or clip, we actually use a VLM for that, right? We use a VLM here, and we are, unfortunately, obviously, are not the first ones to think about this, right? So physical intelligence actually was like 3 months faster than we were, and like amazing work, right? So they actually like did exactly that. They combined basically a diffusion hat or flow matching hat with a VLM backbone, and that works great, right? Similar, like all the follow-up work, right? Pi 05, also Pi even now until Pi 07 and so on, it's still basically VLM plus diffusion hat, right? But one question is, how can we in academic settings do this, right? Because if you look at the models, also at that time, right, they're like giant. We cannot retrain them, right? So, and this again goes back to the question, why didn't you train your own VLA so far, right? So now you know already how to make like diffusion more efficient, right? So through like a mixture of expert denoising, for instance, right? You know how to deal with sparse data or sparsely annotated data thanks to MDT, right? You know what kind of diffusion to use for needing fewer inference steps, right? All of this. But now how can we actually use backbones more efficiently, right? So the VLM backbones more efficiently. And this is what Flower does. So let's first go through the different ways of how we can integrate VLMs and flow matching, right? So we can do early fusion. What that means is that, again, as you know, diffusion basically is an iterative process where we try to remove noise with every iteration. So if we do something that we call early fusion VLAs, we basically retrain the VLM not to produce actions, but to produce the noise that we remove, right? So every time we go through the VLM, we get like this little bit of delta noise that we remove. And you can do that, but it's a horrible idea, right? It's basically ruining the environment, right? Because this is like completely unnecessary, right? At the same time, you can do late fusion VLAs, which is also good, right? So the idea there is that you take your instruction, you take your scene, you go once through the VLM, you take the output, right? And then you basically use this as a conditional on your diffusion hat, right? And then you have a diffusion hat, like a transformer or whatever, that does the denoising with like cross attention in there. So why is that not a good idea? I mean, this is how a lot of the work, a lot of the VLA work started, right? Or people used it. But I'm telling you, I think we can do better. What do you think is wrong with this? You might know, you might not know. Do you see anything wrong with it?
You have to pass through the whole network of the VLM and it's slow.
Sure, but that wouldn't be a problem, right, if you needed to, right? So like if there's just no other way, right, then you only pass through it once, right? So the answer was like that you have to pass through the whole network. I think the real issue actually goes to like if you analyze the VLM. If you actually start looking into what a VLM does, right, internally to some degree. Let's say, for instance, I'm like a VLM right now, right, and you ask me, hey, Rudy, what color does Serena's t-shirt, or what color is Serena's t-shirt, right? You ask me that. At the beginning, right, on the same scene, you might also ask me like what color the chairs are. You might ask me what color the walls are. You might ask me how many people are here, right? Like how many blank faces I'm staring at right now. Like all these kind of things you can ask me, right, for the same scene. And I'm trained on all of these questions for the same scene, right? So in the beginning, I actually first encode abstract information about the scene as a whole, right? So somewhere in my latent space, there is like some part that reflects the color of the chairs, some part that reflects the color of like Serena's t-shirt, some part like that reflects the number of faces that I recognize, these kind of things, right? That happens somewhere in the middle, like somewhere within the VLM. Does it make sense? However, I asked you specifically about the color, or you asked me specifically about the color of Serena's t-shirt, right? And that's the answer that I need to give you. So now from all of this general information that I got, I'm going to boil it down, remove the part of the state space or the latent space that I don't care about, and go all the way towards black, right, as the output, right? So at some point, I'm taking basically this abstract knowledge in the VLM and start boiling it down just to predict the next token. Does it make sense? And this is what also our friends from OpenAI figured out and said basically like, okay, so a lot of the last couple layers of a VLM are just there for next token prediction, right? However, if I actually want to train behavior on this, and I take now this last piece of it, right? I like want to move in here, and I removed a lot of information that would have been super valuable to have, right? So I kind of first need to untrain all of this next token prediction scheme, right? Does it make sense? And that's a huge pain. why not just use this intermediate layer where there is already this information, maybe in an abstract way, but it's also the general information of the scene and not just what we needed for the next token, right? And this is what we call intermediate fusion layer. So this is one of the core contributions of Flower, what it makes it so efficient and so small and so and working really well, right? Like and so efficient in training. So we actually chop off like part of the VLM. In fact, we're using in particular Florence V2 here and chop up 50% of the VLM, right? We can talk afterwards on the coffee break why specifically Florence V2, even though it's aged, is a really good choice here, right, for this kind of scheme. And I can give you the details of that. It has to do with the way that the encoder-decoder stages are trained, and Florence VLM is one of the few models that actually still have like encoder-decoder structure. And then we basically combine this with a simple flow matching denoising process, very similar to what we've seen earlier today, right? So we use this for cross-attention, and we connect those, and that's it. That's what Flower does. In addition, we do something called global space ADA-LN. So adaptive layer normalization, how many of you know what adaptive layer normalization is? We'll see this in the tutorial later, right? But the idea is this is one way of modulating your parameters. Basically meaning that this is one way where we have like some kind of conditional variable, right? Or some kind of information, and we can choose this to adapt what the output of our model would be, right? And usually when you do adaptive layer normalization, you have this like a projection network per layer, right? And we just say like, we don't need this. We're gonna use one single projection metric or projection model, right? Or network for all the layers. And that's why it makes it global and more efficient. We use this basically to determine the action space because Flower is now also, because of that, able to do cross-embodiment or cross-action spaces, right? So when you tell it do the same thing, but you have two arms, or do this thing, or you have one arm, that's the reason why it actually works, right? Again, efficiently. So here on the right-hand side, you see a little benchmark, or like a spider plot across different benchmarks, where each different data corner here is a different, well, like test suite, task suite used in the community, right? And blue represents Flower's performance, outer is better, and the other colors are some of our competitors, right? We even had to bring Microsoft Research on here onto this paper because we ourselves were simply not able to run the baselines, right? Our Flower was completely trained and done on in-house, but the baselines for these benchmarks. So now the amazing thing here is that Flower is not only small and efficient, right? Small, you can see here the VRAM is roughly double the size of the parameters, so we have less than 1 billion parameters. So who thinks 1 billion parameters is a lot? Yeah, see, when I was a PhD, 1 billion sounded like ridiculous, right? But it's indeed not that much, right? Because like you can run this type of model on a 3090, right? Or a 4090. So, and the other thing is that we actually can pre-train our model much, much faster, right? So we pre-train it in only 200 GPU hours on Droid and other parts of yeah. So and this allows us to do things that the robot was incapable of doing before. For instance, the robot was never trained in lighting conditions like this, right? So before we introduced VLMs as backbones, that kind of shadows would have completely destroyed the performance, right? Same for distractors, right? Additional objects in there, if you have a small model that wasn't based on like a strong backbone, then you basically would overfit to the objects that you had, so any additional distractor would completely performance again, and you would not be able to generalize. And Flower is actually, to the best of our knowledge, the first European visual language action model, which sounds like a brag, right? But it's not meant to be. Maybe a humble brag. But what it actually shows you, right? What it actually shows you is that we can do it, right? And not only can we like do it like in Europe, we can do it in academic settings, right? We can do it, we just need to think out of the box. We need to think a little bit differently and so on, but there's like, I hope that if I see all of you again in a month, and I will ask like how many of you did train your own VLA or came up with your own ideas how to make VLAs better, that all your arms go up, right? So that's basically what I'm trying to do. Okay? So it's not that like, of course we're proud that we're the first European VLA, but it's a little bit of a pity that we had to be the first, right? That nobody else like did something like this. And this is because we tell ourselves that we cannot do it. We can and we should, and we have to. Okay? You have to, you're the future. So follow-ups, XVLA, great work, pretty much Flower plus soft prompting, which is really, really nice. But we want to be honest here, right? so there's no free lunch. So the model overfits to fine-tuned, like to the tasks that it was fine-tuned on. But it overfits very efficiently, right? So with only like 4 to 6 GPU hours and 40 minutes of demonstrations, right, we can actually get performance of these models, like on, for instance, the kitchen tasks. So these kind of things that we've seen here, different tasks in this toy kitchen, 40 minutes of demonstration, 4 hours for fine-tuning, right? We can, we learned 20 skills out of that and solved it very, very efficiently, right? With very high task performance. So it's not a spork yet, so it's not spoon, fork, and knife at the same time, but it's more like a Swiss Army knife, right? Like, so we have the foundation model that we can pre-train it on, and then with only 4 to 6 hours, we can actually fine-tune it. And what this should tell you, or give you an idea now, is where the journey goes next, right? So instead of having a generalist flower, right, we're actually going towards a bouquet, right? So something where we have like multiple experts, right, for different tasks, and we combine them or orchestrate them in an agentic way, right? And if you want a new task, you provide some demonstrations. It sees if it knows how to solve the task with the skill set that it has already. If not, it's going to a new one. So coming soon. Okay, so how much time do I still have left? I have time. Okay, good. We're not done yet, right? Because I want to give you more examples of how we can actually think out of the box and can actually make contributions or impact in the community, right? So the next thing I want to talk about is Beast. So what is Beast? Beast is an action tokenizer. So why do we even need an action tokenizer? Because I already told you that we need to somehow represent the actions to the robot that the robot is doing, right? So let's start with VLMs and tokens. You have an image, you have a query, you're going to ask your like VLM something about this scene, right? So why is Tartarsaurus so happy, right? And then it says like, okay, so like we're going to put this into a visual language model. Let's say you already have a little bit of context, so you already have a little bit of output on there, right? So previously the model already produced the tokens because Beast changed her, and then now the question is, what is the next token? What would be a good fitting next token here? And this is what we do through scores. So each color here represents like a high likelihood of this token or low likelihood of this token. So for instance, like posture would make no sense here, right? So that's like the model doesn't even give it like a high likelihood, right? Or a high score, I should say. But mind makes a lot of sense, right? Because Beast changed her mind, right? So this will be the next token. Tokens don't have to be full words. Tokens can also be partial words, punctuation, all kind of things, right? But in general, it's a discretized like action space, right? So you actually have like this cross entropy loss that you use here for the next token prediction scheme. Sense? And with this, basically, we update that the sentence mind comes like as the next word here, and we basically continue. So this is roughly the idea how VLM works, how the scores or how the scores affect the token selection and so on. So when we talk about now tokenization of actions, we talk about how we can go from continuous multi-degree of freedom trajectories towards like this discretized scores that are understandable or parsable for the model, right? Does it make sense? But we could use just binning. So you could just discretize it, but it's a horrible idea, right? It's not very efficient, and it doesn't really work for more complicated trajectories. But you can do something else. You need to find a lower dimensional tokenization, right? Like a lower dimensional space where there's like better information content. And again, our dear friends from physical intelligence did amazing work here, right? Called FAST. And the idea here behind FAST is that it's described, like they basically put the trajectories through a discrete cosine transform and then use byte pair encoding to reduce the number of tokens, right? And that improves the learning speed significantly. However, it becomes very slow, giving like quite an ironic name. But still great work, right? No question there. So something that bothered me a little bit is that discrete cosine transform and byte pair encoding, what do we know it from? Where have we seen this? Computer science students. MP3, JPEG, or right? Like this is stuff that people use for information compression, right? Like in a lot of domains, right? Well, we're in robotics. Why don't we use our robotics knowledge to solve this problem, right? And that's a little bit which I find a lot in the community right now in behavior foundation models. People look at vision and at language, right, which is great, right? But we're solving robotics tasks. So we should come back to the stuff that we know of robotics and see how we can leverage that in order to make these models better, right? Make sense? So what we did instead is we looked at this and said like, well, a lower dimensional representation of trajectories, we do this like since decades, right? It's called movement primitives. The idea is that if you look at the like purple line on the very top image, right? It's a straight line. However, it's an actual linear combination of those basis functions on the bottom. But for any time step, you sum up the value of each of those basis functions, you end up at that line. Does it make sense? So now what it means is if I play around with the basis functions, right? I play around with the amplitude of these basis functions, I can make arbitrary trajectories. So I can now have like a sine curve here, right? Which basically like means that I now have only to worry about 10 parameters here instead of the whole trajectory, which is de facto a reduction of the parameter space, of the trajectory space, right? And then you can reproduce like a slightly smoothed version of the trajectory, which by the way is good because a lot of data that we're mimicking, that we're doing imitation learning on is quite noisy. So smoothing it out is not a bad thing. Make sense? So, and that's all we do. That's what Beast does. We use, to be clear, not Gaussians as here, right? But we use B-splines. But the idea is, in a nutshell, we have those basis functions, and instead of tokenizing the entire trajectory, we first use rich regression to project it basically on this parameter space, right? Very simple rich regression. Like you can do it like that, it's done, right? So on the data set once, like this is a pre-processing step, right? And then we basically just discretize the amplitudes. Sense? Okay. So now instead of Gaussians, we use B-splines. Why do we do this? Because I told you that the trajectory is a linear combination of those basis functions, right? A linear combination of B-splines is, make sense? How many of you are familiar with B-splines? How many of you are roboticists? You should all be familiar with B-splines. We do B-splines for decades, right? B-splines are super nice, have a lot of nice properties. Let me give you some of the properties. I can guarantee, right? It's mathematically guaranteed that the control points of the start and end point here, right, will overlap with the final trajectory. Make sense? I can further guarantee that this trajectory will never leave the convex hull. Basically meaning that whatever the highest and the lowest point is a natural boundary for my trajectory, right? And this holds in multiple dimensions too, right? So also, I can guarantee smoothness because the derivative of a B-spline is a B-spline, right? So we basically do position and velocity, and we always have pinpoint accurate transition between those, right? And I can compute them like that, right? So there's like basically no compute. It's all a mathematical mapping, right? We have very fast tokenization. We have semantically meaningful tokens because the control points live in the same space as the trajectory itself, right? We increase learning speed significantly, and we also increase inference much significantly. So we actually can do up to, like with a naive Python implementation, up to 60 hertz inference speed, right? Whereas our competitors are between 5 and 10. And it's not just us saying this. There is, like I'm first going to show you some of the performance, right? So this is basically over training steps, over fast and 0, right? Our setup here, well, but I want to focus on. So on the top, what we see, let me pause this. Top, what we see is two variations of and Beast is just a tokenizer, right? So we can use it in a normal diffusion task, or we can use it in a flow matching, or we can use it in ACT, or we can use it as a VLM tokenization, right? So without flow matching even, just next token prediction with those Beast tokens, right? So Beast F basically would be a VLA, right? Not a VLA flow matching, a VLA with Beast tokenization, and Beast D would be. On the bottom, we have pi 0, and we have pi 0 fast. What you will see is, we spend a lot of time tuning. Still amazing work, no question, right? But, right, like, so there, yeah. So I just think it makes sense to look a little bit into the community where we actually are and do things many decades, right? Instead of just always looking outside of the community and seeing in. So, and then Beast follow-ups, there's like the work of Omnisat, and what is nice is basically that they reproduce our results and show that we're every time basically better fast or equal at least. And what Omnisat does is that it takes Beast and in addition puts BPE on top. Right, pair encoding compression here. Yeah. So with this 3 very recent works where I don't have like great slides, but I think also again important to show you. So the idea is that, like I mentioned, interpretability, right? So we're asking ourselves, can we actually have like an intermediate layer between the VLM backbone, right, and the action generation part that we can interpret, right? So we actually go towards affordance graphs and say like, okay, we take a model that just trains as it does, right, as normal, and then we co-train basically this scene graphs or affordance graphs in there, right, and see like what the model thinks is important. So this doesn't prevent the model from overfitting or doing anything like this, right? The model still overfits, but now we see it. Now we can actually see in the graph, because we can highlight it, which modes or which like objects the model thought were important, right? And this is not that the model tells us, because this would again be like subject to hallucination, these kind of things, but it's actually that we can like see this in the structure of the latent space. Because we structure the latent space as a graph, and the action generation is purely done on the graph. And as we presented this recently at CPR, but I think this is, again, one more example of how we can actually do research that becomes relevant, that is a little bit outside of the mainstream, right? But still plays in. And the next thing is our newest VLA called DAM VLA, which in hindsight isn't the best naming, because after we put it in archive, we saw that there's like 10 other DAM VLAs. So like, yeah, it's a sought after name. But the idea here is actually, again, to look into how these models work these days, and can we do something to make them more efficient or like change them in a particular way. And what we thought of here is that if you think about introducing additional modalities, additional sensor information, right? So usually you're on a clock. So your information, your camera images come in with like 10 hertz, 15 hertz, 30 hertz, whatever, right? Then it goes through the VLM backbone, and then it goes into the action head, right? And then we produce the action. Make sense? Right. However, sensors come in a different pace, right? Sensors come in like force sensors we can do 200 hertz, right? These kind of things. Proprioceptive information is whatever the speed we want it to be, right? And we shouldn't only act on what the state is right now, right? Like after this clock. But we should instead like separate the incoming information and the information that we act upon. What is decoupling, right? We want to separate the belief state that we have, similar to what humans do, right? I'm just making this claim, I'm not like expert, but this is my understanding, that we act a lot on our belief state instead on directly on our sensors. Does it make sense? So this is what DAM VLA does. DAM VLA actually separates the loop in which we produce actions, right, from the loop where we incorporate new sensor information. We do this by introducing separate buffers for different information, all right? And basically have these buffers, the recurrent buffers here, determine themselves what the information is relevant to keep for the next, whenever the next action comes, right, or the next action is requested. In this way, we can actually integrate, for instance, force feedback with 200 hertz into the action generation, right? Well, the QR code points towards the website, so please go ahead. Fast. Here is, in general, how can actually incorporate how often you press the button, right, of the soap on the right-hand side, and also like if the Lego block already is properly in there, and like all these force information that usually gets neglected. Oh, I should have said, why does the force information often get neglected? Because forces come at a peak, right? If you do something, like you manipulate something, the force information is doesn't stay constant for like, let's say 30 hertz, right? So by the time between two images, the force information is gone already. You got your force sensors gave you a new state, right? So because it's much, much faster. So by the time that you look at your new image, like maybe relevant information got discarded already. Does it make sense? And now we basically keep this. Now we're able to keep this information in the loop. Another approach that I think is also relevant for you is basically the spatial temporal reasoning capabilities. I touched on it a little bit in the beginning, right? And there's this issue that right now spatial temporal reasoning of these VLMs, even though we claim they have some reasoning capabilities, is not good. It's really not good, right? So what we do instead is that we actually designed a new complete auto-annotation pipeline that is able now to do spatial reasoning on the data set itself, right? And create spatially relevant annotation. Make sense? What do I mean by this? So oftentimes, your model is trained on language annotation that is augmented, right? So if I'm at the left of something or the right of something, right? Even if an image I'm only on the left on, I can flip the image and make it on the right on, right? So what this turns out to is then if you actually look at the latent space for these two different instructions, you end up with like a cosine similarity, which is different at a 6th point after the comma or something like this, right? So they look like for the model, for the latent space, those two on the left of or the right of look very, very similar. And there's a bunch of benchmarks that actually show exactly that, right? So, and with this idea of actually saying like, oh no, we're gonna distinguish from like what was said to what was manipulated, because this is what we actually look at. We identify which objects for a given instruction have been manipulated and how they differ from the other objects, right? I can show you here, right? We actually create now data sets that when trained on, we improve spatial benchmarking from 10 to 70%. So it's an idea, right? All of what you're seeing, by the way, is automatically generated, right? So if you, for instance, get a request to put a striped towel, very commonly, this exactly happens, right? So your VLM actually identifies a bunch of objects as being striped. Then you have to figure out like, okay, which one is the correctly feasible one and so on, right? So, but this is of course like very, very bad, and this is because it doesn't really have like spatial understanding. It says like grab the striped towel, maybe you mean the one closest to the gripper, right? Or more often than not. We actually are able to now automatically dissect those and create those. With this, I'm at the end. And I think I'm actually overtime maybe even. Oh. Yes? Okay. So there's more work to be talked about, but I want to invite you all to actually come on board. Let's destroy these barriers together and show that we actually can also contribute. And start thinking out of the box. Start thinking as roboticists and not computer vision or language processing people, right? Nothing wrong with that, but we have valuable knowledge, right? We should use that. Thank you.